Okay, YouTube, in this video we're going to focus on is the general term of an arithmetic sequence. And that is to say the general term would be something that, say for instance we had a sequence that started at 2, this is our first term, and then we have a common difference of 3 every time. So this would be like 2, 5, 8, 11, 14, and so on and so forth. The real question is, like, could we come up with a rule for just like the nth term so that if I wanted to say find the 25th term, I could just tell you just by plugging in 25 that right there is the output. And so that being said, let's go ahead and kind of explore what we have here. Of course, our first term is 2. If we were to find the next term, we would understand that we would really get 2 plus our common difference here, 3. So in this case, of course, we get 5. If we were to look at, the third term, really we get 2 plus 3 plus 3. I'm going to write, plus 3 times 2. I'll write it that way. And then like our fourth term here would be like 2 plus 3 plus 3 plus 3. So, plus 3 times 3, something like this here. But here's giving me my 5. I'm getting my 8 here. I'm getting my 11 here. Basically, though, what you're seeing is as we keep adding on another 3, this number here that we're taking times our 3 is just kind of like going up by 1 every time. In other words, our first term is what we start with, and then we keep adding on another d every single time. And so one thing that I want to kind of point to here is this, that our first term had no d because we hadn't added anything on yet, a common difference. But our second term is a1 plus d here. Our third term is a1 plus 2d. Our fourth term is a1 plus 3 times d. Basically what I want to point out is this, like in a3 here, our third term, that 3 down here, our n, that 2 is always 1 less than, that 2 happens to be 1 less than that. Or our fourth term, the number that is the coefficient of our common difference that we're adding on to a1, that number there is always 1 less than the term number. So 1 less than 3 here on our third term would be 2. 1 less than 4 here on our fourth term would be 3. In general, we could say, well, then what would be true about the nth term? Well, observing this general pattern, then we could say that in general, and I know that this, I'm writing it again here, what this says here, we say the nth term, but we'd say it would be our first term plus always 1 less than the term number times whatever the d is there. And so this is going to be our general rule for the nth term. And this is something we want to memorize, basically. And so the good news for this is that, the nth term or the general term of an arithmetic sequence whose first term is a1 and common difference is d is this. And it just basically means that what we need in order to write the rule are going to be a1, which is our first term. We need to know the value of the first term to write a rule. And we need to know d, which of course is our common difference, or if you're looking at the graph of this would be like our slope here, okay? And so let's go ahead and take a look at how we could use this rule. But one thing before we start using it, let's go ahead and point this out. We'd say our output, or what usually we used to call y values, but in this case is our a sub n. Our output is equal to starting at the first term plus what we're changing by every time times n minus 1. And so one thing that I kind of like to do is this. I like to write it this way instead. And there's just really no wrong way to write this. It doesn't matter what order we multiply in. But really I like to do this because I'm clearly stating that, hey, start here and then add on this amount, like this many times is what it's saying. And so when we look at this next set of checkpoints here, it says find the 9th term of the arithmetic sequence whose first term is 6 and whose common difference is -5. And so if we wanted to do this here, essentially all we would have to know are the first term and the common difference. So it says find the 9th term. Okay, we want to find a9, but basically of the arithmetic sequence whose first term is 6. And so we were told that the first term is 6. Matter of fact, I'm going to write 6, and then whose common difference, I'm going to write this down here, is -5. One thing I want to be clear on is this. This is our first term. If we're going down by 5 every time, I could go do this. I could say 1 went down by 5, go down by another 5, go down by another 5, another 5, another 5, another 5. I'm going to keep doing this. I'm going to stop saying it though because I don't want to say it. We got 1, 2, 3, 4, 5, 6, 7, 8, 9. Guys, we're going to get this -34. But imagine if I had asked for the 19th or 29th or 900th term. Basically what we're saying is if we were to know a rule, and that's what we want here, a rule for the nth term, then I could go ahead and just plug in the term number and tell you what the output would be. So the way we're going to do this is we're going to say our first term, a1, plus our d times n minus 1. And we don't plug anything in here for an and n here. But basically, let's go ahead and plug in our first term value here. So we say starting at 6 and changing by, and it looks like we're going down by -5 every time. So -5 here. Basically, what I'd like to tell you is that this is the rule right here. Now what we want to do is simplify it. So simplify the right hand side. And so basically what I mean by that is we're going to get an still, but we get 6 plus, and we're going to distribute the negative 5 here. Interesting story is that makes this a negative 5n, but this a positive 5. And so our final rule, I'm going to write this over here, we say an is equal to, it looks like negative 5n is how I'm going to write this, and then 6 and a 5 would give us 11. And so you can see that this would be like a line. You know, you could go graph a line like y equals negative 5x plus 11, which would have a y-intercept of 11 and a slope of negative 5. The sequence is going to do the same thing except for it be a series of dots starting at the first term and only going out for finite, or not finite, but whole number term values that are positive. So let's take a look at another example, which we're going to model with some arithmetic data here, but finding a rule and how that's helpful. So it says, the data in figure 11.4 show that in 2010, 16% of the U.S. population was Latino. And so we can see Latino here. It says that 2010, this is the purple data here. Looks like we have 16% here. And then we have our 2050 projections, which all of these go up except for the white category here. Interesting. But we'd say, okay, so on average, we say this is the it is projected to increase by approximately 0.35% per year. And so what we want to do here is basically write a formula for the nth term of the arithmetic sequence that describes the percentage of U.S. population that will be Latino n years after 2009. And so what we're going to start here is with this. We're going to basically say that in the very, very first year, they have 16%, and this is in 2010, 2010. And what I'm going to really write is that this is our first term. But our next term would be like 16.35. And our next term would be 16.35 plus another 0.35, 16.70. And our next term, and you can kind of see how this is going to keep going up, 17.05, and so on and so forth here for these respective years. But the thing that we want to point out here in this particular situation is that this is the year down here. This is the input year. Okay, so first year, second year, so on and so forth after 2010. And then what we have up here is basically the population. So we say Latino population. And so that being said, what we could do is we could write a rule in general that would represent the population over time. And so all we would need to know, this is the cool thing about it, is the first term and what it's changing by. And so for part A, it says write a formula for the nth term of the arithmetic sequence that describes the percentage of the U.S. population that will be Latino n years after 2009. So we say percentage of Latino population, pardon me, that's supposed to be percentage of. And so we'd say the percentage of, we'd say just the nth term here, would be what I started with, which was 16% plus 0.35, because we're going to represent this as a decimal here. Well, not represented as a decimal, but it is a decimal percentage. And then we would say times n minus 1. And this is basically it. You guys, we want to simplify this though. So we say 16 plus, and distributing this, we'd say 0.35 n minus 0.35. And if we combine this and this here, we would get 15.65 plus 0.35 n. And so I'm going to say that this is our an. I'm going to put a box around this, and I'm also going to rearrange it. I'm kind of OCD like that. So basically what I mean is I like it to look like a linear situation. That is to say, I like to write this as a sub n is equal to 0.35 n plus 15.65. And so we're going to write a box around this, and what we're going to say is that this is the percentage of population Latino, and then we would say number of years after, and I believe it was 2010 that we started looking at this data. So that being said, letter B here says, what percentage of the U.S. population is projected to be Latino in 2030? So the nice thing about it is I don't have to write out 30 terms of the sequence to tell you that. We could just say, well, then we could plug in that term value, A30 here. We get 0.35 30 times plus 15.65. And so using our calculators here, which would be a wise thing to do, let's go ahead and turn this on. We would say the value of the 30th year afterwards, after 2010. Sorry, this is in 2030, and we did start in 2010, didn't we? So I apologize that our n value here is supposed to be 20, and that would be the year 2030, which is 20 years after 2010. So we're going to replace this with a 20 here, and I'm going to try this again. But essentially, let's go ahead and try this. We say 0.35, so on 0.35 times 20, and this is plus 15.65. Enter. So we get 22.65 So A30, or the 30th term, is 22.65. And we could answer this question with a conclusion statement, but we'd say that 22.65% Latino in 2030. Cheers.